Hi, I'm Zhao from the Biostatistics department. In this presentation, I'm going to talk about the collaboration work with my advisor, Dr. William. The topic is about reproducibility, and our work is statistical methods for replicability assessment. Reproducibility is very important in scientific research. It's a characteristic of the correctness for scientific discoveries. And irreproducible findings can be misleading and erode public trust in science. There is also a growing awareness of the irreproducibility issue in the scientific community. The phrase replication crisis was coined in the early 2010s as an indication for that. And we also have this MIDAS reproducibility challenge to call on people's attention on it. However, despite the importance and the rising awareness, the foundation of reproducibility is still unsettled in the literature. So we still have the following challenges. First, there are general confusions in the conceptual definitions for different modes of reproducibility. For example, the terminologies like reproducibility, repeatability, and replicability are often used interchangeably in various contexts without clear distinctions, which makes the communication on reproducibility very vague. Secondly, we lack the consensus on specifying replication success. So it is unclear that under what kind of criterion we can say a finding is replicated successfully. And because of the ambiguity of the above two, rigorous statistical methodology for assessment are also lacking. We will demonstrate our solutions to each of the challenges in this talk. First, we propose a classification to distinguish different modes of reproducibility. This classification is motivated by the Goodman et al. In 2016, but it is more precise and statistically oriented. We classify reproducibility into three mutually exclusive categories by emphasizing the interplays of data and methods. The first mode is methods reproducibility, which refers to the consistency of the results that are generated by the same set of data in the same method. For example, when a researcher can successfully redo the whole analysis of a published paper and also obtain the exactly same result, then the findings of the paper are method reproducible. Therefore, method reproducibility can also be called as repeatability. The second mode is inferential reproducibility, which is the consistency of the findings for a scientific question when researchers apply different methods on the same dataset. Although we are not aware of it, we are actually evaluating the inferential reproducibility each time we utilize the same simulation dataset to compare two methods. The last mode is results reproducibility or replicability, which refers to consistent results obtained from applying the same method on different datasets. For example, most of the systematic review is actually evaluating the replicability of the findings. We will focus on the replicability in the rest of our talk. So before defining the replication success, we first look at some inference principles. Because the results are generated from different data sets while evaluating the results reproducibility, the variability actually lies in the different data sets. And that variability is from a combined effect of two components. First, the different underlying true effects, and second, different experimental noises. The two components actually play different roles. First, we claim that the replicability assessment should only focus on the underlying true effects. However, assuming identical underlying effects in different datasets is too restrictive and unrealistic. Therefore, we should define an acceptable extent of variability on the underlying true effect. Meanwhile, the experimental random noise should follow a non-informative principle. Consider extremely noisy observation, then it should contain no information for replicability assessment, but not evidence against the replicability. So with this inference principle in mind, we could review the commonly used criterion in literature which defines the success of replication based on repeated statistically significant results. For example, repeated small p-values. However, by doing so, it actually violates the non-informative principle. For example, if in the first original experiment, we obtain a significant result for the effect of interest, and in the replication study, assume the observations are extremely noisy, which leads us to an insignificant result, then we will draw the conclusion that the original finding cannot be replicated. However, it's not valid since the replication study is too noisy to be informative. So by reflecting on that, we propose a directional consistency criterion, in short, DC criterion, to define replication success. So it says that with a high probability, the underlying effects of the replicable signals are expected to have the same positive or same negative sign across experiments. So this criterion emphasizes on true underlying effect and could help us to specify a range of acceptable heterogeneity by defining tolerable probability of sign consistency. And it could provide a baseline for assessing heterogeneity. We implement the DC criterion to parametric models. Before talking about the statistical method, we first look at the two potential application scenarios in reality, which is the two-group scenario and exchangeable group scenario, respectively. So the two-group scenario refers to one, the original study and the replication study follows chronological order of data generation. So the scientific question would be whether the results derived from the replication group confirm the finding from the original experiment. Many recent systematic replication attempts actually fall into this category. For example, there is a project called Reproducibility Project Psychology. The authors gather independent data sets and also carry out independent analysis, try to replicate the original results that were published in the psychology journals. And also we have exchangeable group scenario. It refers to when a group of multiple experiments is gathered and they don't necessarily have chronological order. And the scientific question under this scenario is to assess the overall concordance of all the experiments, for example, in systematic review. We developed the model criticism strategies combined with the DC criterion to evaluate replicability under both scenarios. So this model criticism procedure is as follows. First, we define a family of reference models to describe the replicable signal. As we mentioned previously, we already parameterized the DC criterion in parametric model so that we can describe the replicable model by defining parameters that correspond to high DC probability. Then we will fit the observed data. In our case, it's the estimated effect and also the standard error to the reference model. Finally, we apply Bayesian prior or posterior predictive checking procedures to evaluate the goodness of fit of the data to the replicable model. And the prior or posterior predictive checking procedure are designed for the two-group scenario and the exchangeable group scenario, respectively. The resulting metric we could obtain from applying the algorithm, the criticism algorithm, are the prior or posterior predictive replication p-values. In short, we call it prior posterior PRP, and also the corresponding 1 minus alpha predictive interval. Worth to mention here is that the prior PRP is calibrated. Therefore, it is uniformly distributed under the reference model. And also there is equivalence between the replication p-values and the predictive interval. A pool fitting, for example, if we observe small replication p-value, it is actually indicating incompatibility between the data and the replicable model, meaning the rejection of the observed data are likely to be replicable. So let's take a look at the usage of the proposed method by the reanalysis of the RPP dataset. As mentioned previously, this RPP is the Reproducibility Project Psychology. This project attempts to replicate 100 psychology studies published in 3 top psychology journals during 2008. In the media report of the RPP results, because the researchers focus on the repeated significance, therefore, more than half of the scientific research results are reported as irreproducible because the p-values in the original psychology paper passed the 0.05 significance level, but the replication experiments failed to reproduce that significance. However, because we don't believe the repeat significance criterion are valid, so we redo the analysis by applying our criticism method. The plot shows evaluation on each individual study. So the original estimated effect in the psychology paper is represented by a vertical tick here. And the filled dots, either red or blue, are estimates from the replication studies, which is produced by the RPP project. And the studies are sorted by the increasing prior PRP values. The red dots are from the studies that with the prior PRP smaller than 0.05. And we can see that they also falling out of the corresponding 95% predictive intervals, which is shown as horizontal lines. And we can see that our method marked only 15 irreplicable experiments, which is much fewer than the original RPP reported. We could have a more clear picture of the overall assessment by looking at the histogram of predictive replication p-values. As we mentioned previously, the prior PRP should distribute uniformly under the replication model. Therefore, the overall trend is alarming because here we see a clear positive skewness, not uniformly distributed, which indicates irreplicability issues overall in psychology. And our method could also investigate specific mechanisms of irreplicability by constructing different test statistics. So if we use the publication bias specific test statistics and regenerate the prior PRPs, we could see an even more worrisome trend. So we can look at the purple histogram here. It is more right skewed. This actually suggests publication bias can be the main source of that irreplicability in psychology research. So everything discussed in this talk is covered by this archive manuscript, and the approach is implemented in the R CRAN package named PRP. Thanks for watching.